So we're on this journey to figure out why oils and water don't mix. We know these are both important in cosmetics. Many cosmetics, like soaps, want to remove oils, and then you have other cosmetics that want to put oils on the skin or keep oil in the skin. And so, to really understand how soap and lotion work, we need to understand how and why things that are opposite, polar and nonpolar, don't mix, and then ask ourselves, is there a way where they can mix? And we'll answer that in the next screencast. So, we've been going on this kind of journey of why do polar and nonpolar molecules not mix? And if you just kind of look this up, it kind of has this throwaway sentence, like dissolves like. And basically what that means is that polar things or polar molecules mix with other polar molecules, right? And then nonpolar molecules, I said things before, probably should have said molecules, mix with other nonpolar molecules. So polar things mix together and nonpolar things mix together. But that's not all of it. The reason this happens is that molecules that have similar polarity, and we spent 2 screencasts talking about polarity, is one component, but they also have to participate in the same type of attractive forces, will dissolve each other or mix with each other, okay? Well, what are these attractive forces? Well, the attractive forces that we're talking about here are what's called intermolecular forces or intermolecular attraction. This is the attraction between molecules. So when we talk about intermolecular forces, right? And if we were to define it, it would be the force of attraction between molecules. Okay. Now, in the previous module, we talked a lot about intramolecular attraction. And intramolecular attraction just means the attraction between atoms, right? So if we're talking intramolecular here, this is between atoms. So like a covalent bond, which is shown here in hydrochloric acid or HCl, versus the weak intermolecular attraction, which is between molecules. And so what we have here are 2 molecules of HCl. Now, a lot of times this type of attraction is shown with a dotted line here, this intermolecular attraction. So these attractive forces can be divided into 4 categories. The 4 categories are London dispersion forces. Now, London dispersion forces are kind of funny in that they have a synonym, and so they're also known as induced dipole interactions, okay? And you'll have people even shorten them more to just dispersion forces or just London forces. The second one is dipole-dipole interactions. And it's important for you to write it twice because it requires 2 polar molecules. And so writing it twice helps us remember that. So we have dipole-dipole interactions. The third is hydrogen bonding, which is a special type of dipole-dipole interaction. And then the fourth is ion dipole interactions. And these are actually really critical for soap. It's one of the reasons that soap forms and can be dispersed in water. So these are the 4 that we're going to talk about, and we're going to define them and talk about them in depth in just a little bit. But I want to give you a few things just kind of as an FYI. London dispersion forces here, this is the weakest. Okay. Ion dipole, this is the strongest. And the way they're listed here is their strength increases as we go from London dispersion to ion dipole. So it will go London dispersion, dipole, hydrogen bonding, and ion dipole interactions. So this is the weakest, this is the strongest. Let's jump in and look at these different ones, okay? So the first one we're going to talk about are London dispersion forces, which are also known as induced dipole interactions. These attractive forces occur when electrons become unevenly distributed over a molecule's surface. Okay. And so when this happens, so if we look here, we have these two atoms. And so we have just two normal atoms of helium. Okay. And there's no difference in charge. Okay. And then something happens to make these two electrons run to one side here. When it does, it induces a partial negative charge just on one side of the atom. Now, these atoms come in contact with each other and sort of like peer pressure, right? If this is negative, it's going to repel these electrons and send them to this side over here. And so now we have this weak attraction between these two atoms that are nonpolar. And so because one side is partially negative and one side's partially positive. This is called induced because it's not permanent, right? This is not a permanent dipole. So we spent a lot of time talking about permanent dipoles, right? In the previous screencast, it's induced because it is not permanent. It's there for a little bit and then goes away. Now, a few things about this. All compounds have London dispersion forces. But they are the only intermolecular force, I'm going to abbreviate intermolecular force as IMF, that nonpolar molecules have. So if you can identify a molecule as nonpolar, the only intermolecular force it's got is London dispersion force. Okay. It is our weakest intermolecular force. And I want to talk to you about a real life example where you will encounter this. You have encountered this probably most often in your kitchen, or if you've worked in service before, and have ever used saran wrap or cling wrap or some sort of plastic wrap. So when you have plastic wrap is a long non-polar hydrocarbon chain, and it's got an even distribution of electrons. So cling wrap here is just carbons and hydrogens, and we know that's a big nonpolar molecule. When you pull cling wrap out, though, there's just a momentary disturbance of the electron cloud, where all the electrons travel, or most of them, to one side of that molecule. And so that means it's partially negative, and the other side is partially positive. And so then across that cling wrap, it will attract each other. And that's why your cling wrap ends up looking like this when you pull it out, right? So that's the reason that cling wrap sticks to itself, is because of these London dispersion forces. There's no other reason there. Now, we're going to focus on some intermolecular forces that polar molecules can have. So polar molecules are going to have London dispersion forces, but polar molecules can also have dipole forces. These forces are due to these permanent dipoles. You can identify them because it's between two polar molecules. So we spent a lot of time identifying polar molecules, and polar molecules have dipole-dipole forces. These are stronger than London dispersion forces. You can see some examples of this here. For example, we have HCl. It's got a partial positive here, a partial negative here. We've got a dashed line that's showing this attraction between these two molecules. Dipole-dipole, only going to be here in the polar molecules. These nonpolar molecules right here will only have London dispersion forces. Right? The polar molecules can have additional things. They will have London dispersion forces, but they can have dipole-dipole forces. Now, these two particular molecules, water and ammonia, can also have a special type of dipole-dipole interaction, which is called hydrogen bonding. Hydrogen bonds can occur between a fluorine, oxygen, and nitrogen on one molecule and a hydrogen bonded to a fluorine, or a hydrogen bonded to an oxygen, or a hydrogen bonded to a nitrogen on another molecule. The way to remember this is chemistry is sort of like fun, right? F-U-N, but not quite. So we can say maybe chemistry is like FON, F-O-N, right? And that's when we have hydrogen bonding, when we have lots of FON. So I want you to look at hydrogen bonding for just a second. When we look at hydrogen bonding, particularly at, for example, this oxygen here, what's really coming here and doing the hydrogen bonding, right, is that you have a lone pair on the oxygen. That lone pair on the oxygen is forming a hydrogen bond with the hydrogen that's on another oxygen, okay? So we've got an oxygen with lone pairs, electrons, that's forming this bond with the hydrogen from the water. This is a sugar molecule. They're showing some hydrogen bonds, but it can actually form many, many hydrogen bonds there. Here's some other examples of hydrogen bonds. You can get hydrogen bonds between, I've got the oxygen here with the hydrogen bonded to an oxygen. Same thing with the fluorines and nitrogens, but it doesn't have to be the same fluorine, oxygen, or nitrogen molecule. For example, you can have a nitrogen here with a hydrogen bond to an oxygen on a hydrogen on an oxygen molecule, okay? So it doesn't have to be one and the same, it just has to be one of those. Then our final intermolecular force, which is our strongest, the intermolecular force, is an ion-dipole interaction. This occurs between an ionic, right, compound and a polar molecule, okay? Now, I want to talk about ionic for just a second. Ionic can show up a couple different ways. It can show up just like, for example, NaCl, right? We've got a metal, we've got a non-metal. It's that ionic stuff that we learned in Module 2, right? And something that's polar. The other way it can show up, or that you'll see it, is with a charge and something that's polar. So like sodium and water, or chlorine and water. Or what we're going to look at in just a little bit when we get into soap is we're going to look at a charge that's on part of that molecule. So this is the way you can see that. Now, when we think about this ion dipole interaction, we're messing with sodium chloride here. We've got chlorine with a negative charge. When you think about the structure of water and we think about that polarity, right? Oxygen's more electronegative. Hydrogen is more electropositive, right? I want you to notice that right here with the chlorine, it's the hydrogens that are oriented towards the chlorine because they are partially positive. And we know positives and negatives like each other. They're attracted to each other. Compare that with the sodium here. That sodium is positive. These oxygens are negative, and they're attracted to each other. And so this is what we see here. So all this to say, so now we've talked about polar and nonpolar and all of these interactions. How do we predict solubilities? Well, let's talk through the three here. So let's talk about nonpolar compounds first. So when we talk about nonpolar compounds, a lot of times these are going to be oils, okay? Oils are going to be long chains of carbon that might have an oxygen in them, and we're going to talk a little bit more about their structure there. So oils are attracted to neighboring molecules right, which are other oils. When I say neighboring molecules, that's other oils through London dispersion forces. Okay. Water is polar. Right? And interacts with other substances through dipole interactions, hydrogen bonding, and ion dipole attractions. Now, water also has London dispersion forces, but it's so weak it doesn't really matter. When we compare these two forces, right, the intermolecular forces these have are very unlike each other. Okay? And so what that means is that water is more attracted to other water molecules through all of these interactions than oil. And so that's why water and oil don't mix. Okay, so we're not going to see that mixing there. Okay, now let's talk about polar compounds for just a second. When we talk about polar compounds, a really good example is right here. This is a sugar. It's sucrose, right? And we have hydroxyl groups of sucrose. So hydroxyl groups, we'll talk about that more when we talk about functional groups. For right now, if I say hydroxyl, that's just the OH groups, right? And so we can look here, and there's lots of these OH groups on this sugar that can interact with water, right? So the OH groups on the sugar, right, make it a polar compound. Right? And give it the ability to interact with water through dipole-dipole interactions and hydrogen bonds, right? So because table sugar and water are both polar and they share these attractive forces, that sugar is soluble in water. So because both water and sugar, in this particular sugar, sucrose, are polar and share these intermolecular forces, they mix, right? So they mix with each other, okay? Now, when we talk about ionic compounds, right, basically what happens is that when multiple water molecules interact with an ion, right? The sum of these attractive forces is greater than the strength of the ionic bonds. And so through ion dipole interactions, water or polar things and ionic compounds can mix, okay? Now, this process is called hydration. If you have taken, though, another chemistry course, I want to point out that there are some ionic compounds that don't completely dissolve in water. That's really outside the scope of this course. That's not what we're interested in. But I did want to acknowledge it in case you're like, hey, I think I've heard about this before. Okay, so I want us to do an example. Okay, right? Predict which of the following compounds will be more soluble in water. We have vitamin C, which is also known as ascorbic acid, and vitamin E here. Both of these are found in cosmetics, in different cosmetics, depending on what the different outcome is hopeful there. So when you're asked to predict if a compound will be more soluble in water, the first thing you need to do is kind of take stock of the question and say, hey, what do I know about water, right? And when we're talking about solubility, the big important thing here is that water is polar. And so we want to figure out, hey, look, which one of these guys is going to be more polar, okay? And you should have a lot of tools in your toolbox already from the previous couple screencasts to be able to look at this and say, hey, look, I think this one might be more polar than the other one. So the first thing I do is I look at this and I say, well, there are no charges here, so we don't have to worry about there being any ion dipole interactions. And so now with these big molecules, what I'm really interested in is these oxygens, right? Because these oxygens are the things that can form hydrogen bonds with water and ion and do go through those dipole-dipole interactions. But carbons are not going to do that. So if I have lots and lots of carbons, that's not going to have hydrogen bonding, and so it won't be as soluble in water. So in the previous one, we said a really quick way to do this was to look at the number of carbons. Now, this is probably the first time you have seen a stick structure, so I want to point something out here. At every point, there is a carbon. We will talk about this more in another module, but I wanted to point that out. That means there's a carbon here, 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 here. Okay, and on this structure, there's the carbons. Okay, it's just a shorthand for us to tell where those carbons are. So when we look at this, I can look at vitamin C and I can say, hey, look, that molecule has 6 carbons to 1, 2, 3, 4, 5, 6 oxygens. That's a 1-to-1 ratio. For every 1 carbon, there's an oxygen. And that guy can form lots and lots of hydrogen bonds with water. Vitamin E over here only has 2 oxygens to lots of carbons. I'm not going to count them, but you can count all those blue dots to your heart's content. So when we look at this, we can say, hey, this guy right here, it's going to be more soluble in water because there are more oxygens per carbon to form hydrogen bonds with water. Okay, and so this is the way that we can use this idea of polarity and intermolecular forces to be able to predict solubility. Now, we will do more of these in class, so if you're feeling a little shaky or you want to see some more examples, we will do more examples in class, and as always, feel free to pop by my office.